So Will, the floor is yours.
Thank you. Thanks for the introduction, and thanks for coming to my talk today. So in this talk, I'll be presenting an experimental study of investigating the turbulent structures over waves. Before we move on, I'd like to acknowledge our PhD student Tungu Biriwara and the postdoc Dr. Kevin, who contributed with some of the results and the data set which we'll be discussing in this talk, and also our collaborator, Professor Mike Benner from the UNSW. Right, so let's start with the why do we need to understand the turbulent flows above the wind-driven waves. Why is this important? So when wind blows over the water surface, due to the friction in the air-water interface, there is a turbulent boundary layer formed on the water surface, which is often referred as an atmospheric boundary layer. And this turbulent airflow actually causes the waves on the surface. So these wind-generated waves can be actually quite commonly observed in our day-to-day life. For example, when you go out on a walk, on a nice day, you see ripples on the lake surface with a light breeze. The ripple is actually formed due to the turbulent flow blowing over the water surface. While this the scenario is quite different in the wind sea, in the ocean, where the wavelength is much bigger and the wave height is a lot bigger than the ripple. Another good example is under the extreme weather conditions, such as a strong tropical storm, creating a huge waves with a complex ocean surface and can cause the greater damage. But the role of this turbulent flow blowing up above the water surface is not only the visual creation of the waves. The turbulent flow is involved in the wave generation process, as well as the wave growth mechanism, which is directly relevant to the sea drag coefficient. And also this turbulent motion also governs the air-sea interaction and the dissipation across the thin air-water interface. So this problem is pretty important to have and important to have a better understanding of those turbulent flows above the wave surface. So in the literature, there have been some studies highlighting the importance of the turbulent flows above the waves. The study done by Moon et al. 2007 showed that the wind stress parameter in the storm surge modeling from different turbulent model can affect the prediction of the wave height by 3 to 4 meters. And this difference is actually quite significant for the wave height forecasting. And also, Donnellan 2018 stated that having a better sea drag coefficient or even better understanding of the sea drag coefficient as a function of wind speed will improve the prediction of the tropical cyclone and its associated effect. More recently, as we know that the turbulent wind input directly affects the wave height growth rate. We conducted a laboratory experiment to study the wave growth rate of the sea state wave field with under the various wind input, and shown that there's an exponential growth rate of the wave height as wind speed increases. So this result is further discussed in the Lee and Monty 2020. And while we were measuring the wave profile of a single wave height as the waves were exposed to the range of wind speed, we started to interest in how this turbulent wind is actually related to or affecting the wave growth mechanism as the fluid dynamicist point of view. So as you may all know, that there are a couple of theories explaining the wind wave generation and the growth mechanisms. And two of those commonly known theory are Jeffries and Miles. So just quick the brief on those theories. So Jeffries' mechanism state the flow separation behind the wave crest cause a pressure difference between the windward and the leeward side along the wave. And this pressure difference leads to the wave growth and the exchange of momentum from air to water side. While Miles' mechanism is based on the implicit flow model with the shear flow instability at a critical height, where the height is where the wave speed is wave traveling speed is the same as the wind above it. So the main difference is that the Miles theory doesn't consider the effect of turbulence on above the waves, and hence there's no flow separation. So this wave growth mechanism has been the active area of research, and believe that both theories play some roles in the wave growth at a different stage of the wave development. But it is still critical to have a detailed flow structures around the wind-generated wave to investigate further of that complex interaction between the turbulent flows and the wave, such as like data set like this. So I'm just showing you that the captured detailed turbulent flow features marked as a color contour, and the gray region is detected wind-generated water wave surface. So with the development of the flow measurement technique, This allows to capture the detailed snapshot of turbulent boundary layer above the wind-generated waves. So this advanced flow measurement technique is called particle image velocimetry. So basically using high-power laser and the high-resolution camera to track the tracer seeding particles that following the turbulent motion in detail above the wind-generated waves or moving waves. And the advantage of this PIV technique is that we can visualize the flow above the wind-generated wave and also obtaining the spatial information data set. So here are some examples of the turbulent flows captured above the waterways. The top one is the Buckley and Veron 2017, and the bottom one is our own measurement capturing large field of view over 3 wavelengths. So the detail of this PIV measurement that we captured, that we acquired, can be found in Kevin et al. 2018. And I will not go much in detail, but this measurement was taken in one of our wind wave interaction facility at the University of Melbourne, which has a 60-meter long working section and has a capability to generate the wind speed up to 20 meters per second. So back to the flow field. So this is instantaneous streamwise velocity field above the wind-generated wave, the water wave, highlighting that. And the gray region is again detected the wind-generated surface. So one distinct feature that catches our attention as a fluid dynamicist is that there is a momentum deficit behind the wave crest, denoted as a blue color contour, which indicates or often used as a sign of the strong flow separation. So if you highlight the region where the velocity deficit is captured behind the wave and plot the velocity vector, which are composed with the streamwise and wave normal velocity component, you can clearly see that the flow recirculation is happening behind the wave crest, indicating that there is a flow separation behind the steep waves. Another turbulent feature to detect whether the flow is separated or not is the vorticity. So due to the natural unsteady nature of the flow separation, it causes the turbulent wake behind the crest, which indicated by the strong vorticity at the onset of the flow separation. And these detailed flow information can be analyzed or obtained when one has a high fidelity large field of view turbulent flow data set like this that we are just presenting. So as we flip through more velocity field, there are lots of turbulent flows that separate from the surface behind the steep waves, as all those fields have shown that strong vertical structure and the velocity deficit. And when we had a careful look, we often realize that there are some smaller surface wrinkles, also known as the gravity capillary waves, are appearing with the flow separation or strong vorticity. So we noticed that this strong flow separation is closely associated with the parasitic gravity capillary waves. Hence, we started to get interested in what is actually the role of these small-scale waves residing on top of the dominant wave to the overall turbulent flow field, and which support the growing awareness of the smaller scale waves contribute significantly to the sea drag and the momentum exchange. So by the way, all this data set that I've been showing so far is been done on the wind-generated waves. So the waves are continuously moving and evolving as the turbulent flows are interacting with it. So now we want to understand whether there's any relationship between those small capillary waves and the turbulent flow structures such as flow separation behind the crest. But as we all know that this is extremely challenging problem to investigate, because when the turbulent flow and the water waves or water surfaces are continuously interacting to each other, inducing the constantly evolving and the moving wave surfaces, it's really hard to isolate one problem to find out what's the role of those, just to single out the effect of small capillary waves. Hence, our approach is that in order to isolate the effect of the smaller capillary waves on the turbulent flow structure, we came up with a simplified wind tunnel experiment with a solid wavy surface with and without the ripple, reconstructed from the wave profile shape that obtained from the previous PIV experiment. So in order to obtain the representative wave shapes, we collected or we detected the wave shape that had a flow separation at near the wave crest, and we conditionally averaged those steep waves. And once you average all this the steep wave profile, the red line shows the converged or representative wave shape. And once you obtain this representative wave shape, we then can add those parasitic capillary waves that we observe in the real wind-generated wave case. And the top plot shows the wave profile, the side view of the wave profile with them without the ripples, along with the dominant wave. And the bottom figure shows that the reconstructed solid wave surface tile as individual tiles. And the left figure is only composed with the dominant wavelength. So we had a smooth at the surface with the wavelength. However, the right-hand side figure, we introduced the ripples at the leeward side of the wave profile on the same the dominant wave. All right, so these reconstructed solid surface tiles were manufactured, and the wind tunnel experiment was conducted in the University of Southampton as a part of collaboration. So this wind tunnel has a working section of 4.5 meter length, and the unique feature of this wind tunnel was that the working section actually can be covered by various surface roughness type, in this case, which is solid wave surface. Also, this facility was actually equipped with the floating drag balance, which is a benefit for us, so that we can get the direct measurement of the drag coefficient for different surface type. So this plot is just showing that the experimental setup in the wind tunnel, covering the working section with the solid wave surface tile. And again, we use the PIV technique with a high resolution camera and the high power laser to capture the detailed turbulent motion above those surfaces. So just highlight that we ran two different series of measurements. So one is just with the smooth dominant wave surface, and the other one is same dominant wave, but we introduced the small ripples at the back of the wave facing. So quickly go through the experimental parameters. The one thing we would like to highlight is that the extensive range of wind speed was used, and the solid wave surface were exposed to the wind speed ranging from 10 meters per second to 26 meters per second to see any noticeable trend or different flow features between the smooth waves and the ripple waves as we increase the wind speed. So here I'm just showing some examples of instantaneous streamwise velocity field from the wind tunnel experiment. So the flow direction is from left to right, and there's a wind speed indicator here. And the left figure will show the smooth wave and the captured turbulent flow above it as a color contour. And the right-hand side will be showing the ripple case throughout this presentation. So when we look at those instantaneous flow fields at the wind speed of 10 meters per second, we noticed that we observed a similar velocity deficit as we observed from the wind generated wave I showed earlier. And this was actually indicator for the flow separation. But as we increase the wind speed to 18 meters per second and 26 meters per second in the instantaneous field, we noticed that the velocity deficit region for smooth waves was a lot less compared to the ripple wave case. And this indicates that the flow is likely attached to the surface for smooth wave with the increasing wind speed. So it might not be quite obvious from the instantaneous field. So here what I'm showing is I'm showing the average, especially average wave field. So in the PIV measurement, we collect over 1,000 images of the turbulent flow for each wave cases for the various wind speed, and then we average them, especially for a given wind speed. And now, if I can get your attention within those the white boxes, we're focusing on the velocity deficit region behind the wave crest, and starting from 10 meters per second to 14, 18, 22, and 26. We notice that the blue velocity deficit region actually reduces in the smooth wave case, while the ripple wave cases remain nominally constant. So let's just quickly flip through it one more time, 14, 18, 22, and 26. And this indicates that, again, the flows, for the smooth wall case, the flow separation was a lot less. So now what I like to do is we attempt to detect the flow separation directly, the separation point directly, by going through the velocity field near the wave surface and detecting any negative velocity vector, which indicates the flow reversal indicated by this arrow here. So when we detect the negative velocity on the wave surface, we mark that as a flow separation point for the range of velocity that we tested. All right, so the thick solid line highlights the detected solid wave surface, just a wave profile. And the location of the wave crest and the trough are marked by red and blue dashed line respectively. And the red circle symbols indicate the most detected separation point using the flow reversal detection method. And then for the ripple case, that shaded area highlights the area covered by those small ripple at the back. So if we plot this detected separation point as a function of wind speed ranging from 10 to 26 meters per second, it is evident that for the smooth wave case, the separation point got shifted towards the wave crest, but while the ripple case was consistently behind the area covered by those capillary waves. Hence, for the smooth wall, we found that the separation location varies as well as the number of the separation event reduces with increasing wind speed, and less separation event means that the flow is more attached near the surface. Whereas for the ripple case, the flow separation point is more or less the same as it separates behind the area covered by ripples, and the flow separation was consistently observed for the wind speed, the range of wind speed that we tested. So quickly, with the drag balance that was implemented in the wind tunnel experiment, we get the direct drag coefficient measurement as a function of wind speed for smooth waves and the ripple waves. Here, the blue circle indicates a smooth case, and the red star shows the ripple waves. And with this increasing wind speed, it is obvious that there are two opposite trends of drag coefficient is observed for the two cases. The smooth wave shows the drag increasing with the wind as the flow is more attached to the surface, whereas the ripple case showing the constant decreasing drag coefficient with increasing wind speed as the flow separation is consistently occurred behind the wave. So it is worth highlighting that the only difference between the two cases was the presence of that small ripples at the leeward of the dominant wave. That's the only difference. All right, so let me quickly summarize today's talk. So we clearly show the evidence that the flow separation is occurred behind the steep wave with the help of the high fidelity PIV dataset. And we observed that the flow separation was closely associated with the capillary wave near the crest. So in order to identify the role of the capillary waves on the flow structure, we conducted the wind tunnel experiment with a solid wave surface and found that the small scale capillary wave actually locked in and induced the strong flow separation. So in the literature, there is a growing awareness of the importance of the small scale waves on the sea drag and the momentum exchange. And our experimental study shows that the presence of these capillary waves indeed have a significant contribution to the turbulent flow structure, such as flow separation, and hence the drag coefficient. So with that summary, I'll take any questions. Thanks.
Yeah, thank you very much, Will, for the very interesting talk. Yeah. All right, so are there some questions? So we have 2 to 3 minutes. Okay, so let me start. So just a question regarding the experimental setup. Obviously, it's very challenging to measure. Or at least I found it challenging to measure the vorticity or the water surface. So how do you do that? And my second question is related to the waves generated there. So because this fetch is relatively short, so what are the waves, the highest waves that you can generate within the limited fetch and with the highest wind speed? Thanks.
Sure. So the first question is that, yeah, so the vorticity is a bit tricky to calculate because it relies on the velocity gradient of the field. And that's why I was emphasizing the importance of having a high resolution or high fidelity PIV dataset. So if you have a well-resolved the flow features above the wave, then there will be the accuracy of the vorticity plot is a lot clearer, or evidence is much more clearer. That's why we spend, like to achieve the great dataset. It's just enormous effort to get it right in the first place. And the second question is with the theory.